Great. Hi everyone. So, I was here and it was asked like JP is like, okay, can you also talk at the social? I'm like, yeah, sure, I can talk at the social. And then earlier today, I'm like, so what kind of people are coming? So the answer was it's diverse. So I'm trying to give an intro into LLVM. I tried to keep it short because I know there's pizza coming, and I'm going to talk about one or two things that may or may not be interesting to you. And I hope that everyone takes something out of this. Feel free to interrupt me. Feel free to ask questions at any point, right? For the people that saw me talking yesterday or today, you might have seen some of it, but repetition is always great. So let's get started here. This is my my disclaimer slide that I always put in, but I actually mean it. I'll give these talks for whatever reason, but there's a lot of people involved, especially in LLVM OpenMP, and a lot of things that talk about oftentimes relates to OpenMP, LLVM, on mostly the combination thereof. And yeah, so we have industry, academia people, we have power users that contribute way more than I do. I'll just happen to be here. Who am I? So as already said, I work at Livermore now. I worked at Argonne before in Chicago. Now I work at Livermore, which is in the Bay Area, so East Bay. Did my PhD in Saarbrücken. Worked on LLVM during my PhD and before. Work on OpenMP since 2018. So when I graduated and joined Argonne. And since 2021, I'm officially the LLVM OpenMP offload code owner. So kind of, I'm at least interested in anything that has to do with GPUs in LLVM, one way or another. And it's not only OpenMP, but anything that does GPUs, because we, as the Department of Energy in the US, we care a lot about computing. When computing right now means GPUs for the most part, so we care a lot about GPUs. We also care about CUDA, HIP to some degree, SYCL. Come in, sit down. Don't worry about it. I haven't started yet. So everything that has to do with GPUs, but I also care about various other topics in LLVM. So I do interprocedural optimization. I also, in my spare time, play language lawyer for LLVM IR. So what should LLVM IR mean? What should it not mean? How can we extend it, and how shouldn't we extend it? So if people want to touch the LLVM language reference, I get a little itchy, and then I look over it and I try to steer everyone, keep the ship tight in the right direction. I'm not the only one doing that. There's a couple of people, and it's good that there's diverse views, but that's fun. Let's talk about LLVM. So this is the LLVM social, so I figured like you have heard of LLVM, which doesn't stand for anything anymore anyway. So for a few years we shed the acronym, it's just a name now. What is it? It's an open compiler. It's an open source compiler. It's an open community. It's an open whatever. So we have a lot of things, but the main thought, if I think about it, is everything is open. So we have meetings, we have virtual meetups, we have a community, we have forums, we have chats, we have whatever, and everything is open. You're allowed to change things, propose things, tell people that their idea is not good without with adhering to the code of conduct. So you can say, I think that idea is bad. That's fine. Preferably tell them why. That's more helpful. But it's open. So open is good to some degree, right? And for me, the alluring part is it's extensible. So if something doesn't work, so my app is slow, my like use case doesn't work and so on, I can go in and actually fix it. If you know a little bit of C++, you can go in and you change the code. And preferably then you turn around and you try to upstream it. Best case, you actually talk to people first, figure out the design of your change, if it's non-trivial, then do it, then upstream it, but all of it is doable. It's kind of portable, so you can target at least all the for me interesting CPUs and GPUs with it. Though we're working on things like targeting Apple GPUs, targeting Intel GPUs, which we currently can't do, but it's on the horizon. It supports all the programming languages that you may or may not care about, especially everything in the C language family, right? So everything that looks like C and smells like C and quacks like C is supported by Clang. And all the other languages, you know, Julia, Rust, Python, actually use LLVM or can use LLVM. So if you're interested in, you know, combining some Julia code with some C++ code and some Fortran code, LLVM IR is probably your best bet for that. It's obviously, you know, has the coolest features that go into the standards because people have to write them first somewhere, and LLVM is a good candidate for that. So new C++ features oftentimes appear or are at least available in certain branches. I mean, I put this in, it's obviously performant and correct at all times. I mean, how could a few million C++ lines not be performant and correct at this point, right? And what might be interesting for you if you want to contribute to LLVM is that it is the basis for almost all vendor compilers nowadays. So it doesn't matter which vendor compiler you think of, they use parts, if not all, of LLVM's toolchain. Some are in the transition and some have like multiple alternatives, but everyone is using it. Okay, so this is a screenshot of the LLVM monorepo that we merged all our little repositories at some point and we made a monorepo, which is great. It actually has benefits, and well, let's see what is in there. So for everything C star, every C family, you have Clang lives in there. You have the compiler runtime to do sanitizers. Sanitizers are great. If you don't know about sanitizers, I would recommend start reading about and using sanitizers because they help you find errors before they actually, you know, bite you, and they help you localize errors. And there's various kinds of sanitizers, and they're really good. So if you ever use Wallgrind during your development cycle, you might want to switch to sanitizers instead because they're better. We have a modern Fortran frontend, which used to be called F18, but given the fact, you know, Clang is called Clang, you know why, right? C lang, Clang. So Flang has to be Fortran. The Fortran compiler has to be called Fortran lang, Flang. So Flang is dead. Long live Flang is a thing that I will print that on a T-shirt at some point when the thing is up and running, because this is iteration number 5 if I didn't miscount. So this is the 5th new or completely different thing that is called Flang. Some of which you can actually find, and people are using them right now. That is not this, so it's cool. This one was called F18 at some point, and it actually is in a better shape than people think. So it can actually do quite a lot of things in terms of CPU programming, and there's proof of concept for GPU programming as well, and so on and so forth. We have our own C++ standard library, which is an alternative to lib standard C++. I mean, we can spend all night arguing which one is better, but they're different, and you know, alternatives are good. Competition is good, so it's good that we have that. We have a linker replacement. So there's, if you ever, you know, run into the problem that your linker uses too much memory or is too slow, which a lot of people do, even if they don't realize, I would recommend using, you know, LLV first. And if you really need fast link times, there's even, you know, faster ones afterwards. But LLV gives you a nice balance between, you know, all the features that 99.9% of all people care about, but fast. We have an LLVM-centric debugger, which replaces GDB. You see the idea here. So we take things that exist and we make them new from scratch, for better or worse. This is where I spend my time, this and this guy here. This is the core LLVM, as it is sometimes called. That's all of the LLVM IR definition, all of the standard optimizations, analyses passes, and the backends. So everything that generates you target code all lives in there. And then OpenMP runtime, that is, or the OpenMP folder, that is where By now, I think 9 OpenMP runtimes live, so one for the host, one to orchestrate offloading, and then one for each offload target that we support. So AMD GPU, NVIDIA GPU, remote, like distributed offloading into the cloud or some other computer, x86, ARM, vector, NEC vector engine, virtual GPU is not upstreamed yet. Maybe it's not 9 yet. Oh, we're getting there. Okay, so this is just giving you an idea. There's a lot going on in LLVM. So LLVM is an umbrella project of, plenty of things. This is what a lot of people think LLVM is. Other people think Clang is LLVM. All is not, wrong, but there's a lot. So LLVM Clang 101. So Clang is the most user-facing thing we have. That's what people associate with LLVM. It's the C front end, so C, C++, and so on. So you take a file, you run Clang on it, and what you effectively get is the first step. Okay, I'll take one step back. When I say Clang, there's different things that are called Clang. And now we go a little bit into the weeds, but you have to learn something here, right? So now you learn something. So the first thing, that what you call Clang, what you call, like the thing you call there, is a driver. That is the Clang driver. That is not a compiler. That is just a thing that knows how to invoke other things to, make whatever you wanted it to do happen. So that's like level 1. It's kind of like a script that takes your arguments and looks at them and says, that's what you want to do. I gotcha. Okay, so that Clang then calls the Clang front end, Clang minus CC1, to take C code and generate your LLVM IR. Cool. LLVM IR is a low-level assembly-like language in SSA form with virtual registers and a lot of other stuff. And then you can use the op tool, which is effectively just a binary that allows you to interact with LLVM IR naturally to analyze and optimize LLVM IR, right? You can then, the Clang driver will not use the opt executable, but it will directly, do the same thing. But opt is just an executable that gives you access to the LLVM middle end, effectively. All the analysis, all the optimizations that work. And they take LLVM IR and they spit out LLVM IR, which is like one of the differentiating features towards GCC. Back in school, I saw like a paper about GCC where they showed, 15 different intermediate representations that the GCC goes through. And in LLVM, there's not one intermediate representation, but for the entire middle end, there's one intermediate representation. There's some intermediate representations here, and there's this one, which is the LLVM machine IR, which you can use LLC to get there. You can also use LLC to run machine optimization analysis passes on the machine IR. And then you can use it to generate actual, object code, your x86 assembly, whatever you have. I stay here, mostly there. All of this is scary. Just saying. Okay, here you go. This, you don't have to remember this. Point of this is, if you, later look at the slides or whatever, you can build LLVM. Actually, building LLVM is fairly trivial. And now people do that, and then they come to me and say, oh, it takes, 30 gigabytes of memory, and it takes, 12 gigabytes or 30 gigabytes of file system space and 8 gigabytes of memory to build it. And I'm like, yeah, that's a full debug build with all debug symbols and other stuff, and you probably didn't use a good linker, as I said earlier, and so on and so forth. So there's cool options that you can set, and there's, lots of documentation online. You can build LLVM on a laptop just fine. If anyone tells you otherwise, they're just wrong. And you can even set it up such that you can rebuild LLVM if you change something in a reasonable amount of time. What I would suggest everyone here, if you start build release plus asserts, you get almost everything you want. Now, this is a general, technically this is a general, I'm a C, C++, CUDA, or C language developer. What should I do to make sure I am better at my job? This is kind of a cheat sheet of things. Use a faster linker, it makes makes a difference. Use CC cache because it's good. Use Ninja instead of Make because it's faster. Consider link time optimizations if you can. If you can't, consider thin link time optimizations. They will make your code faster. Consider, one of the things I haven't even on here is consider profile guided optimizations, PGO. They will make your code faster. And it doesn't actually cost you much effort in setting that up. But if you care about performance, you should do these things, or at least look into them. If you don't care about performance, forget it. It doesn't matter. Just do whatever you do. O3 is great, but for example, if you don't tell the compiler what your architecture actually is, you get generic architecture settings, which is not good. Because if your architecture supports certain things, you might want to tell the compiler, hey, please, use, generate code for those certain things that are specific. The documentation that is online is not great, but it's also not that bad. Google is your friend. Lots of information also on the forum, and the forum, the people don't bite, and I'll get to that in a second. This thing, back to it's an open community. We have lots of ways for people to get in touch. We have Discourse, which is effectively kind of a forum mailing list thing. Discord, which is a chat app for cool people. I hang out in IRC, which is the chat app for not so cool people. We have weekly, this meeting is, the AA meeting is not for the alcoholics, it's for the alias analysis folks. We meet once every 4 weeks. These guys meet every week. Machine learning in LLVM meets every 4 weeks. OpenMP meets every week, and we actually have multiple meetings. RISC-V, they meet, I don't know, every 2 weeks maybe. So we have meetings about all sub things that you might be interested in, and those meetings are in a calendar, and you can just, join them. You can also download them, and you can just join them, not say anything. You can join them and say something. It's fine, either way. We have office hours. So there's a couple of, let's say, people that have too much time, that offer up their time to sit in a Zoom on a specific date and time, every week usually, every 2 weeks, and wait for people to just call into this Zoom, random people, whoever it is, and those random people to ask questions or bounce off ideas and so on and so forth. And it works. People do that. People call into these Zoom meetings and ask these experts whatever. They ask them, hey, I have this idea, how can I do this? Hey, can I have this code, I want to upstream, or can LLVM do that? And so on and so forth. You can go in and ask anything, and there's quite a few people doing this, so you have selection, also what language you want to speak, what time zone you're in, and what area you're looking at. And those people don't know everything, don't get me wrong, but they probably know what your next step should be, even if they can't answer you, and they can tell you what people to talk to, what to do next. And we actually have meetups again. So EuroLLVM was 2-3 weeks ago in Glasgow. Great. If this is all too much, Getting Involved page on the documentation has links to everything, the calendar and all of it. So, okay. A few things for users especially, but also developers, because I feel like a lot of people that do developing and haven't actually used this enough. Optimization remarks. People know that from the PGI compiler and Integ compiler. LLVM has that too. So you can ask LLVM, hey, LLVM, let the vectorizer tell me what it did, why it didn't do things, and what it thought while doing the things it did. And you get these, remarks. You can even, get files and show these remarks inside of your IDE or inside of an HTML associated with your code, so like inlined in your code with nice graphics. All of that tooling exists, all of that you can do. But by default, you just get it, on the command line, and it tells you here, I can't reorder those floating point operations, so I can't vectorize your loop. Okay. SIMD is the go-to to vectorize a loop. You just plug it on, and if you run it again, it will say, I vectorized this loop for you. Okay, cool. And then if you do OpenMP offloading, this becomes even more critical, because we do very high-level optimizations that are, make or break. your performance. So if you do OpenMP offloading, I would very much recommend to use rpass analysis OpenMP opt and rpass minus mist OpenMP opt to let the compiler tell you if it managed to do things or didn't manage to do things. Now you see this already. I mean, this is kind of straightforward, right? Not vectorized, okay, you know what's going on. You know what vectorized is. Not vectorized, you know what's going on. And you can kind of parse this and you know what's happening. But here, let's be honest, could not move globalized variable. What the F is a globalized variable? To the stack. Okay, I know what a stack is. Variable is potentially captured in call. I can guess what that means, but so there's something happening. Mark parameter as attribute no escape to override. Okay, there's a lot happening here. It's longer, it's more complicated, but it's also like a more complicated high-level transformation. But the trick is, at the end, there is like this identifier here, right? OMP113. And then you go onto our web page. Again, web pages are not the best, but also not the worst. And then you click onto OMP113 here, and it tells you it's an analysis report. You know, you have, oh no, that was the wrong one. Anyway, whatever it was. And you click on it, and then on most of them, you have to see a small example code that shows the problem. And that describes the problem in text, more text, you know, here, this is what's going on, and this is what the problem is, and this is what we're trying to do. And then tells you what you can do about it. Not all of them, but a lot. And some of them also just describe, oh yeah, this is a good remark. If this happens, good. And this is what we did, and this is what we did it. So that's kind of cool. Yeah, but those remarks exist for, you know, other passes as well. Mostly, you know, the inliner, vectorizer, and so on and so forth. All right. Link time optimization, I mentioned that earlier. You really want to do link time optimization effectively. For everyone that doesn't know what they do, they allow your compiler to optimize across two files. Right now, if you have two C files, there's no information transfer from one to the other. That's it. So whatever the compiler knows while compiling one of them, it doesn't know while compiling the other, and vice versa. Why is that so? Because, you know, when we developed how all of this is set up, how we do compilation, how we do, you know, programming, we were in a time where only one file at a time fit into our memory when we compiled it. So that is why we had to split them up. And then and we couldn't keep the information about the file in memory while compiling the other because we only had memory for one file. So come in, sit down. So that's kind of, that's historically the problem. Now, when you do LTO, when you hear LTO, people usually think monolithic LTO, which effectively is take all the translation units, merge them together into one file, and then run the optimizer. That's great. It gives the compiler the best view of everything. You can even do that without LTO when you have like CMake, for example. CMake gives you the option to do, thank you. Unibills. So it effectively, what CMake does, it kind of really copies them together. Like it kind of, you know, copies all the file textually together and then has one file and runs compiler on it. What compilers do usually, they process the files separately and then merge their intermediate representation together, or they put the intermediate representation into the object files, and when you link the object files together, you then link the intermediate representation and run the rest of the optimizer. There's also thin LTO, I mentioned that earlier. It's an LLVM thing that allows you to get some of the LTO benefits, but still parallelism while you do the linking step, so you don't have a sequential link step, which might take too long. What we did recently is we introduced device offload LTO, which is really good, and you really want to use it. And you can actually use it even with CUDA and HIP in upstream. You need to set another option, but technically possible. And then that's good. If you especially if you have GPU code that is distributed over multiple files. That's really a game changer. So we have some numbers here. This benchmark here, for example, and this guy do not actually distribute their code over multiple files, but the fact that we do offload LTO allows us to optimize more. It can also, you know, cause regressions, but that is just an unfortunate side effect of the fact that optimizers don't actually optimize according to real world performance, but according to, they have some made up objective function and they optimize according to that. And locally that looks good. but globally down the line that might actually cause problems. So sometimes you get this, but usually you get improved performance. And if you have actually have code that is split across different translation units and calls into each other, especially on the GPU, your performance improvement for LTO can skyrocket. Even on the CPU, that's the case. So I would really look into that if you're not. I have some slides about the latest LLVM release, but I'm running out of time. So this is the 15 that was like 8-9 months ago, almost a year ago. These are just interesting features for offloading GPU programming that people might be interested. So we have a new unified driver which allows you to mix and match HIP and OpenMP offloading or CUDA and OpenMP offloading. You can embed multiple architectures into one binary, so you can have a single executable and a computer that has an AMD GPU and an NVIDIA GPU and soon an Intel GPU, and you can run with that binary on all of them at the same time. We do LTO, you can do static libraries, and interoperability I already said. And then 16, which was in early this year when we branched it off, you can get a just-in-time compilation for offloading kernels. You can get asynchronous offloading on AMD GPUs. You don't have to specify your architecture anymore. You can just say, whatever the GPU is that I have, target that thing, right? Record and replay allows you to run a huge app and get standalone executables for all the GPU kernels. So if you afterwards want to profile, tune, debug, modify a GPU kernel, that run, 3/4 into your app, that run 5 times, you can then analyze, tune, debug, and modify and whatever each and every instantiation of that thing. You can tweak the code, run it again. I could tweak the LLVM code, run it again, and verify it's still correct, for example. And then you can play around with performance optimizations and so on. It's kind of fun. Where does that go? Sorry. I lost the slide after this. We have a fancy tool that we built, an executable with LLVM that tells you about all the devices you have in your computer. So it tells you, oh, we found 8 GPUs, and those GPUs have the following type and the following architecture and so much cache and so much RAM, and so it tells you like a full report about your devices. And I had a screenshot of this which disappeared. We have tracing support. So you can get like Chrome tracing files by just setting an environment variable, and you get a nice tracing file of your offloading. And the last thing I want to talk about not until pizza, but is direct GPU compilation. I thought we started that. Okay, this is the last thing I have on my slides. Yeah, that will end the talk. So direct GPU compilation, GPU first. I mentioned that earlier today, so some people saw this. The idea is as follows. Everyone has CPU code, right? That's a thing. So you have a legacy CPU code. And now these GPUs, and you kind of want to run your stuff on GPUs for one reason or another. What is everyone telling you? Oh, you have to rewrite your code. You have to either add pragmas, you have to use a different language, CUDA kernels, libraries, I mean, you name it, but you have to do stuff. What if I tell you you don't? Wouldn't that be nicer? So what do? We take the app, we don't change it, we compile it with our Clang, which effectively is just a almost regular Clang, has a couple of neat tricks that it uses, and we create an executable. And that executable is going to invoke your main function, your start of your program, on the GPU. And then it's going to run all of your program on the GPU, beginning to end. And if there's stuff in your program that calls into, libraries, like, I don't know, you call fopen or fscanf or a third-party library, it will take those calls, it will take the arguments and the underlying memory, and it will move it to the host. We'll do the call there. We'll take the result, and we'll copy it back to the device, and you will continue to run on the device. So you can call fopen, fscanf on a device, and you didn't actually change anything, and it just works. So that's the claim here. We can show it works. What we yet can't show is that you get great performance for various reasons. If you write your program as, I start my program and then I have a parallel region, and then that parallel region is going to, run, or everything in my program is parallel, and I have like one big parallel region or multiple parallel regions, you broke it. It will actually be fast. But if you have a program that is the way it usually is, there is a lot of sequential parts in your program, Amdahl's law is going to be really hard on you, because on the GPU, those sequential parts are even slower. So you spend even more time in the sequential parts. So no matter how much we take the parallel parts, we can get them, really parallel on an entire GPU, and we can run them with 10,000 threads. But if your sequential parts make up 80% of your performance already on the CPU, and then we make a factor slower when we run them on a GPU, you will not see performance improvements. You really have to start with a program that is parallel. But what you can do with this, and this is what we did here, is you can do performance estimations. You can check if your parallel regions that you currently have in your CPU programs are going to perform well on a GPU. How's that? You take so these are always bar groups of 2, 2, 2, 2, 2, 2, 2, 2. So you take your CPU code, you compile it onto a GPU and you run it. And what we do is we take your parallel regions and we split them off into separate kernels that run on an entire GPU. And then by doing so, what we can do is we can measure how fast would your parallel region be on a GPU. So if you would offload your parallel region on your GPU, you would offload all the data necessary, and then you would offload that parallel region and run the parallel region on the GPU. We can measure how fast that's going to be. And this plot is there to show you that our measurements, by just doing no code modifications, are actually accurate, because the left side of the plot, like the left of the 2 bars, is always someone had manually ported these parallel region already to the GPU, and they got that performance for those parallel regions on the GPU. And our version is next to it. So here we get a little better performance. Here we match up pretty much exactly. Again, better performance, and we match up exactly. And now the fun thing is, what we could do with our thing is, in these benchmarks here, these proxy apps, there's 2 modes of operandi. So they have a command line flag, and you can say either, please do event mode or history mode for some nuclear reactor simulation stuff. I don't understand it, but it's it computes the same thing in different ways. So there's an algorithmic choice built in, right? But only on the host version, not on the device version. The device version has one choice only, because they didn't port the other one, because porting is effort. So what we could do now is we can just take the host version and we can see how would this history method perform on the device. Will it perform good or will it perform bad? And we can basically estimate how it will perform. Now, full disclosure, I talked to the author of these things, and he told me that in the full application, the history method is ported to the device, and it doesn't perform well. He explained to me why, and he said if these proxy apps had a bigger data set, so we used the 2 data sets that were available, but if he would have provided us a larger data set, we would have seen that it doesn't really scale. And I'm like, okay, but that is just, you give us a new data set and we could have, figured that out. That's fine. But the point is, you can take a CPU app and you can determine, will my algorithm work on a GPU, or do I have to change my data layout, my algorithm, other choices, and you can figure out, does it scale if I keep it like that? And if it doesn't scale, you can easily modify your CPU code and then try it out again. You don't have to, if you change your data layout, if you do offloading, you have to also change all the memory mapping, because now you change your data layout. So you go ahead and you do the entire offloading almost again. And then it still doesn't work, so you do it over and over. It's a lot of effort. And here we did one of those studies that I'm saying. So what you see here is a CPU spec benchmark CPU app, and we increased the input. So this is the input size. We increased that. And what we show here is relative slowdown of the parallel region in that app when run on the GPU versus when run on the CPU. So on the CPU basically is 1, the line 1 here. That's the performance you get on the CPU. And this is slowdown. So it's slower. But it's not about how fast it is, it's about how it scales if you increase your input, right? What you want to see is effectively a line that is flat. Technically, you know, downslope would be great too, but flat is fine. Flat means it scales. So if it scales on the GPU as well as it scales on the CPU. That is what flat means. What you don't want to see is what you see here. That is, it goes up, and it goes up hard. I mean, this looks exponential to me. I'm not sure if anyone else agrees. So that means that while on the CPU, whatever the CPU scaling for this program is, if you increase the input, it is exponentially worse, the scaling behavior on the GPU. So that whatever you're doing there is not well suited for a GPU. And it turns out what they were doing is a producer-consumer communication between threads, which, you know, works for a while and then doesn't. And I mean, you could obviously say, oh, we would have known that, but do you know what all of your codes do? And do you know, even if they don't do like stupid things, do you know if they will scale? You could just try it out. And it's like literally just take a different compiler for your same app and run it. It's as easy as that. Okay, as I said, that was my last thing because I don't want to, you know, bore everyone too long. If anyone has any questions, and feel free to not only ask about the, you know, the slides. I just picked a few. Ask about anything, and afterwards, I hope the pizza is there, right? Yeah, go ahead. Mm-hmm. Mm-hmm. Yes. I mean, you mean these GPU direct take the entire app and just execute them on the GPU? That part, like, yeah, it does. Everyone does. Yeah. Mm-hmm. Yes. Yep. I mean, our right now our offloading stack for OpenMP offload looks exactly like that. I mean, it's you could get rid of them. You can build them statically and actually link the entire shebang, technically speaking, into your app. We do not provide that as a supported method for various reasons. For one, it's a lot of work. For two, for most people that will not really give them a benefit. And three, it's a foot gun. The few people that might use it might shoot themselves in the foot really badly. Why? Because as soon as somebody uses that and builds a library, that library is effectively incompatible with other offloading threading approaches because these things don't know about each other and they can't talk to each other. The benefit of the whole shared library mess that we have, which usually isn't that bad in my opinion, is that you have a library that does offloading and another library that does offloading and you have a program that's offloading, but they will all use the same library that organizes everything. And in having one library in control is the only way to sanely build anything. As soon as you try to have competing libraries for the same resources, you're doomed. The question is, how doomed are you? And I'm not sure what your problem, and later you can tell me what your problem was with the shared libraries. I mean, we have them as well, but we just install and or you set the paths right, and then everything should just work. I mean, there was never really. The only problems that we get is if the people are on a system where there's multiple versions of Clang with OpenMP offloading, and they pick up the wrong set of libraries. But I mean, that is a problem that exists for all shared libraries, and I'm like, we have solutions for that. We just have to employ them. Yeah, go ahead.
Can you tell something more about the new programming language announced by Mr. Leitner?
Mojo.
Maybe from the perspective of the open source, what are they contributing or what to expect?
So I talked to Chris the other day. I was sitting next to him, and I asked him about it. Not what they're contributing, but like I'm like, so Mojo, huh? And he's like, yeah, they're trying. How much of that will go into open source, and how much of their middle end MLIR optimization stuff they upstream, how much of the front end stuff they upstream, I do not know. I expect, just guessing, just me guessing, I expect in the short term very little, because they're a small startup, and they're currently in the news, which means the 80% of the time they reply to emails, or just filter through what they actually have to reply to and what they should throw away. So I mean, I'm making fun, but that gives you the idea. And they will first need to use it and get adoption. So they need to use it to actually, do AI accelerator and get people to use it and get at least, one big backer or something like that. That is me guessing again. Before they will have the time to upstream a lot. They might open source before, but depending on where you are, that might not help you much. I mean, for me, them open sourcing would actually not really make much of a difference, because that's similar to other vendors that use LLVM to build their compilers also open source their compilers, right? Which is great. I mean, that's a great thing, and then people can look at it and so on and so forth. But at the end of the day, I and my users, we effectively need one compiler and not three. So even if their compilers are open source and I can grab them and I can build them, but then they have like this feature that I want, that's cool, and I have a compiler that has that feature, but I also want the features that my compiler has, so then I have like two. So now what do I do with two? So everything that is effectively not in my compiler is of very limited use to me, and it depends on where you are. And long story short, I don't know, to answer your question. Yeah. No. It is, if it, I mean, nothing I do really is, secret or hidden. I'm not sure if the repository is public, and if so, where it is, because one of my students did it. But if you're interested, I'm fine with just giving you access and or making it public and telling you about it. We have also a little bit more write-up about it. Um, we have an early paper from last year that just where you still had to write the stubs for all the functions that have to cross the boundary yourself. So you had to write a stub for the device and a stub for the host for each and every function that you want to, translate over. The new magic that does this automatically is just lives somewhere in our repository for now. Do we want to upstream that? That depends. That depends on how our proof of concepts pan out. If we manage to get to places that are useful, we'll try. We usually upstream I mean, everything that we do that is useful is going to be upstreamed, and everything that we can't upstream is basically abandoned by us, because we can't maintain anything downstream. But it's too early. I mean, this is, out there. We try out new stuff, proof of concept things, and even if we wanted to upstream it, what is more likely to happen is if it works out, we'll redo it in upstream. This is a research prototype. I mean, we cut corners, and then for upstream we can't. But yeah, I'm happy to give people access, and if people want to try it out. And we are currently working on right now on the first, and then we have other ideas on how to actually get performance out of this. I mean, how do you take a CPU app that you have off the shelf that is written for HPC cluster or so, and run it faster than a small cluster on one and or multiple fancy new GPUs? And I think it's possible. But We still haven't done that yet. I mean, the conceptual problem, if you look at it, is a GPU has one GPU requires like parallelism in the tens of thousands, roughly. I mean, if you have like parallelism in the few hundred, you might get away with speed ups, but tens of thousands is good. So that's what you want. And what we currently use is we execute more or less everything sequentially except the parallel regions, the OpenMP parallel regions, which usually they don't provide us tens of thousands of concurrent items most of the time. And then in most of the time, and every time we're not in a parallel region, we have the sequential part. So that's wasted resource. That's not how you program. That's not how you make a GPU run fast. So how do we get more parallelism on a GPU? And we have a couple of ideas, I think, that that will pan out to different degrees on different applications. This is not going to be a one-size-fits-all. The first thing we're now doing is ensembles. A lot of applications, like sciencey applications. I mean, I'm not a scientist, I have no idea, but people tell me that a lot of applications actually, they sample a certain search space. So they have a couple of parameter configurations. They want to run their simulation for, I don't know, gamma between 0.5 and 1.5 and in intervals of 0, 0, 1. So they want to run this space and they want to see how that influences their simulation, right? And the simulation is heavy, and then they have this space of parameters. What if we, instead of running the program once, like one program, like stick thing on the GPU, what if we run 10,000 instantiation of the program on the GPU at the same time? Here we go. We got our parallelism somewhere. We found it in the input space. Like you run your image pipeline on, not one image, but on all the images you have in your library. And then you got parallelism. And maybe that is a way to satisfy, the GPU and get the parallelism we need. There's other ways that I can bring up later if you want, but yeah, so. LLVM IR. Technically, we can there's no connection to Clang whatsoever. So we can take Fortran code, we will. You can take Rust code and Julia code and whatever you have. Yeah. Well, I think. Here we go. Mm-hmm.
Moving data around and how we make because I tried to solve and find resources and I found things that might be helpful, but I didn't get any specific answers as to what is done to solve this problem.
Okay. No, I'm not 100% sure I follow. So you're interested in how would you as an application developer improve your latency for hosted device copies, or what the compiler could do to help you, or what? Okay. The former, assuming you already do everything you do is asynchronous, and in CUDA you pass a stream to everything, and in HIP or whatever, and for us you do everything with no wait and so on and so forth. You already do everything kind of right. I mean, that is from a user perspective more or less everything you can do. There's these high level things. Make sure your memory is if you have a lot of memory that you send, make sure it's page boundary line, make sure it's pinned, make sure stuff like that. So you have these common tricks, but that's pretty much it. If you have a lot of small transfers, you might actually get away with faster runtimes by batching them, by putting them together. I mean, we do that in our offloading runtime. If people pass a lot of small variables to a kernel, and we have to map them through host-to-device transfer, we look at them and we have like a heuristic that decides, you're going to send, 10 different values, all 4 to 8 bytes to a device, and they live at different places, so we have to issue 10 different hosted device copies. That's going to be bad. So instead, what we do is, if you actually copy the value, we read the value on the host, copy them into a struct that we malloc an area, copy all the values in there, and then copy that thing as one go. That can improve your performance. It depends on where you are in the spectrum and so on and so forth. And then lastly, if you think your bandwidth is too low and you already did pin memory and all of the good stuff, you have to talk to the vendors and tell them that their drivers are not up to snuff. On the compiler side, we actually, we did a prototype that unfortunately never got finished. That took asynchronous host-to-device memcopy. Okay, let's say that. And it doesn't really matter which language it is. All of them look the same, right? You say, here's kind of my synchronization thingy, like a stream. Here's my data, or my pointer to the data. Here's the pointer I want it to be copied to, and here's the size. Okay, and then the thingy goes away and enqueues this copy into that stream, and then you continue execution. That's what the asynchronous part does. So you only enqueue the work, and then some driver thread on your, inside your driver does it. Okay, that's cool. Now, what you can do, even if it's not asynchronous, let's even start with the synchronous case, which makes it more fun. So you have a synchronous copy where your host thread actually hits it, and then would do the copy and wait for the copy to finish, and then continue execution, which sometimes makes sense. So what we did in our proof of concept, which unfortunately again hasn't been finished, is first thing first, we split the synchronous transfer into an issue and a wait with a handle. So basically now we made it asynchronous, but we issue and then we wait on the result right away. So far we haven't actually done things. We have made it worse, but that's a different story. So that's what we did, right? So you issue, you wait. But then you can ask, effectively you can then ask your compiler, or you have to implement it, but you can then say, okay, let's try to move the issue up to earlier in my execution path, and let's try to move the wait down to later in my execution path. And everything that is now between the two is now hidden in the during free computation effectively, or depending on which direction you see it. I mean, either somewhere there is something free. That is heavily dependent on how good is your alias information. If the alias information is good, this might, and not only is the alias information, but where is your stuff placed? So if your stuff is placed you initialize the memory, then you copy, then you use it right away, you start a kernel or something, there's no place to move it. I mean, we can't do anything, this is just what it is, right? But if you have, for example, abstraction layers, where somewhere you have a function that says, move this object to the device, and then you do some stuff, and then you call that function from somewhere, and you do some more stuff, and then you call a kernel. That's not that uncommon with abstraction layers and so on. And then there might actually be potential to split it and move it. Why? Because it's really hard as a programmer to otherwise write all of that manually. So that's an option there. But again, at the end of the day, the common tricks, pinning, alignment, batching, and put everything into streams. Even if you just do copy, kernel, copy, instead of doing them as synchronous operations, put them into streams. It's going to be faster, or stream-like objects, whatever you have, right? It's going to be faster. Cool. Sounds good?